all the linear models we have seen so far involved only numerical predictors, but we can incorporate categorical predictors into the model without problem. When we do so, we are not going to be changing the slopes as we have seen so far, we're going to be changing the intercepts. And how we deal with categorical predictors is we add what we call dummy variables into the model, or dummy terms. And specifically, we're going to add one new term into the model for every level of the categorical predictors, or as people like to call it nowadays in computer science, one-hot encoding. By the way, we have ordinal variables that are kind of in the middle between numerical and categorical. Normally what we do is model them as both numerical and categorical at the same time, include both of them in the model and see how the model reacts to those two different kinds of variables. But anyway, let's assume we have one categorical predictor. For simplicity, let's say it's only binary, so we can have only one of two possible levels, either yes or no. How do we incorporate this into the linear model? Well, we do it by adding one dummy variable, let's call it z. And that z is going to have only two possible values, either 0 or 1. And what we do is, if the observation has x equal no, then we have z equal 1. And if the observation is yes, then we're going to have 0. All the other way around, it's the same. So what does the final model look like? Well, let's say the final model would be still a certain intercept. It's always going to be in there. And now we have a coefficient for z. We are not modeling x directly, we are modeling z. And so looking at what z is modeling, then we have these two possible cases. If the predictor was yes, we saw that z equals 0, and so we only have beta 0. The model would be only beta 0. And if we have x equal no, we saw that z would be 1, and so we have the model beta 0 plus beta 1. And so the only difference between having x equal yes or no would be whether beta 1 would be active or not, whether it would be hot, as they would say. And so these are the two possible predictions of the model, either beta 0 only when x equal yes, or beta 0 plus beta 1 when x equal no. So it's essentially kind of breaking the model into two different alternatives, yes or no. What does it look like? Well, let's say we're going to model the wage of employees as a function of insurance, whether they have health insurance or no. So this variable is, again, categorical, is binary. An employee may or may not have insurance. Those are the two possible levels. So the model would be the wage equals beta 0, the intercept that is always there, plus a second coefficient beta 1 times the dummy variable insurance no. So this variable will be 1 if the insurance or the employee doesn't have an insurance, 0 otherwise. So if we do OLS, we fit the model. These are the coefficients we would get from fitting the model. How do we interpret this? Well, beta 0, as we saw, would be the case in which insurance no equals 0, meaning insurance equals yes. So we have the estimate of 124 beta 0. So again, the wage will be y equal beta 0 if insurance equal yes, and we will have beta 1 if insurance equal no. Beta 1 plus beta 0. And so in this case, beta 0 would be the insurance yes. And it's what we here see in the box plot. So this is telling us that the mean for the group yes equals beta 0, 120. And then this beta 1 is actually kind of a deviation from beta 0. It's kind of how much variation do we have for the case insurance no, given the reference. So it's something like starting from beta 0, how much we have to deviate from it when we have insurance equal no. And what this is saying is about 28. So taking beta 0 as a reference over here, if we go minus 28 units, that's what we have the mean for insurance no. And so somehow what this is saying is the model is estimating insurance yes equal 120 and insurance no equal somewhere like 102, because it's taking a deviation of minus 28 from the intercept. And this is how we have categorical variables into the linear model. It's about having one reference intercept, the beta 0, and then deviations from it, 1 for each of the levels of the categorical predictor. So let's say we have more than 2 levels. It's not only yes, no, but something with more levels, like the marital status of the employee. Then what we could have is one dummy variable per level of the predictor. So we could have a Z1 that equals 1 if the employee is married, 0 otherwise. Then we have a second dummy variable, Z2, that is going to be equal 1 if the employee is widow, 0 otherwise. Then we go to Z3, maybe 1 if the employee is divorced, 0 otherwise. And we keep doing that for every level of the categorical predictor. And then now the linear model turns into something like this. We still have beta 0, the intercept, and then we have coefficients for each of the dummy variables. This turns into beta 0 when x equals never married, which is kind of taken as the reference. And then we have deviations from the reference. So beta 0 plus beta 1 if the employee is married. So Z1 would be active, meaning the employee is married, so Z1 equals 1. All the others are going to be 0. If the employee is divorced, then the model is beta 0 plus beta 2, because beta 1 would be 0, beta 3 would be 0, everything else would be 0, only beta 2 would be active, so to speak, or would be hot. And so, again, by adding all these dummy variables, what we're doing is establishing deviations from a common reference beta 0. And those will be exactly the estimates for each of those groups, in this case of marital status. Again, note that only one of these dummy variables, only one of the z's, is going to be active for any given observation. This is how the model is constructed. A person cannot be married and widowed at the same time. Only one of those is going to be equal to 1, so only one of those is going to be adding a deviation from the intercept. What does it look like? Well, again, what we have is a common intercept, beta 0, and then one coefficient and dummy variable for the rest of levels in the categorical predictor. So we have status married, status widowed, status divorced, status separated. We get our data, we do OLS, we come up with a linear model. These are the coefficients. How do we interpret them? Well, again, it's important that we realize that beta 0 corresponds to one base case. In this case, this is never married. And so this estimate, 92.7, is actually the estimate for the first case, for never married. It would be somewhere around here. This is beta 0. What is the average for never married? And then if we have an observation that belongs to another group, let's say widowed, what we have is, in this case, a positive deviation of about 7 units. So it would be beta 0 plus beta 2. That would be the estimate for the group widowed, so about 100. This is saying here, from beta 0, we go plus beta 2, and we have the estimate of about 100. What about separated? We see that there is a positive deviation of about 8.5. So we would take beta 0 plus beta 4 in order to get the estimate for separated, which would be around here, beta 0 plus beta 4. And so again, we have beta 0 corresponding to the average for one specific level of the categorical predictor, in this case never married, and then all the other coefficients have to be interpreted as deviations from that common intercept. So it's not that the average salary of a married person is 26. It's 26 plus 93. And so we have this concept of the reference level, what the intercept is referring to, and then one fewer dummy variable than levels in the nominal predictor. So in the previous case, we have 5 possible levels, but we have only 4 dummy variables because one of the groups in the predictor corresponds to the reference. So this is the reference or baseline, however you want to call it, and all the others are deviations from it. Now the baseline here is the intercept beta 0, what we said, equals to the mean of the first group. Now one might wonder, which should be the first group? Well, this is completely arbitrary. There are sensible choices that can be made based on domain knowledge. Like, for example, if we're carrying out an experiment and then we have a control group and then an experimental group, then one might think, okay, let's consider the placebo group or the control group as the reference, and then we have deviations from it. That makes sense. Maybe our predictor is about the country of a person. Well, which country should be a reference? In principle, there's no order. Or one is men and then another one is women. Which one should be the baseline and which one should be deviation from the baseline? Well, it's completely arbitrary. It doesn't make sense to say one or the other. By the way, there are other ways in which we could model these categorical variables. We have a link over here if you want to take a look. So, for example, one alternative could be that the intercept, the reference, is actually the average, the overall average, and then the others are deviations from that average. So we will have positive and negative deviations always. And there are certain cases in which that makes more sense. But anyway, the typical one is the one we have here. One group as the reference and then all the others deviations from it. Sometimes we might be interested in not having deviations from a baseline, but to having an exhaustive model having one coefficient per level without deviation, so that the coefficient is directly telling us the average for the group or the estimate that will be produced for the group. And we could do that, and it would be about removing the intercept. What does it look like? Well, now the beta 0 is actually the coefficient for the first level. You see that it's multiplying status never. And we don't have a standalone coefficient, a standalone intercept. And so what we have now is that, again, only one of these dummy variables is going to be active at the same time, but the model has no reference. So if we want to estimate never married, it would be beta 0. If we want to estimate married, it would be beta 1, but not beta 1 plus a reference. It's only beta 1. And if we want to estimate separated, it's only beta 4. And so you see here now, the model looks quite different because all these coefficients are actually estimates for the average wage per group. It's not that this is a reference and then all the others are deviations from it. Not anymore. And so what this is telling us is the average or the estimate for the status equal never is 93. That would be over there. And then we have status merit equal 119. So it would be directly telling us this number there. And then status widowed 99.5. So it would be somewhere like, again, over here. So we have directly the coefficients telling us what the estimate for the group would be. Sometimes we might be interested in doing this because it's easier to interpret, to look at. Now, the minute we start adding more and more predictors, what the reference is and what beta 0 is really modeling is going to be a lot more intricate, and reasoning about the coefficients and average for one group or the other and the effect of another variable, etc., is going to be a lot more complex. So my advice is don't do that. Always fit an intercept because it's going to make everything easier later. Just FYI, if you have only one predictor that is categorical and you want to look directly into the estimates of the model, okay, you can do it.